SalienTime provides a novel approach to temporal selection in geospatial systems. Over the past years, geospatial big data, such as observation satellites, meteorological instruments, and numerical simulations, has grown exponentially in both ubiquity and volume. Take the Copernicus Sentinel Data Access Platform, for example. Up to 2022, there have been more than 68 million datasets available and more than 400 petabytes of volume downloads. The full potential of these large-scale datasets can only be realized through efficient approaches to user access. Nowadays, many organizations offer users a web-based data portal, allowing users to explore the datasets without downloading the entire file. Some examples include NASA Worldview, Sentinel Hub EO Browser, and MetOceanView. However, the voluminous nature of geospatial data often leads to cumbersome and blended user experience during temporal selection. Loading a single frame of data may take several seconds. Users often have to face lengthy waiting periods and random navigation between time steps. Identifying which time steps are salient for prioritized preloading and visualization is highly desirable for elevating the user experience for exploring such data. In this paper, we first conduct extensive user studies with 5 experts from the field of geoscience and visualization to understand their workflows and needs when performing temporal selections. We let the participants explore the aforementioned systems freely, instruct them to perform at least one data download, and record their behaviors during the session. The interview is structured around the following outline: their motivation and outcome, the factors that influenced their decision-making process, how they perform temporal navigations, and their overall remarks about the interaction involved in the workflow. This table compiles our findings. Most participants mention the slow response time for loading data and the lack of contextual guidance, making them navigate between time steps randomly in the hope of locating important information. Building on this, we establish a multifaceted definition of salient time steps from 3 perspectives. Summarizability, which are frames that can summarize the critical information and trends within the dataset. Anomaly, which are outliers deviating from the norm. And extremum, frames that represent extreme values within a certain spatial and temporal region. We aim to select a subset of time steps as salient frames by combining these 3 perspectives, considering structural similarity, statistical variation, and distance penalty. We now elaborate on each of these cost functions. First, for the structural cost, we leverage a CNN-based autoencoder to lower the spatial semantics within the data and produce a low-dimensional latent code for each frame. We train our model by using the decoder to reconstruct the original data frame and employ a discriminator to further supervise the reconstruction quality, encouraging more meaningful latent codes. The latent code is the concatenation of the output after each convolutional layer in the encoder. The structural cost is then computed using the cosine distance between the latent codes. The statistical cost computes the difference of aggregated values between 2 data frames, using aggregators including max, mean, and average, helpful for revealing the extremums and anomalies. Users can switch different aggregators to suit their needs and adjust the weights of statistical cost and structural cost in the system. Additionally, we incorporate distance cost to prevent selected frames from being concentrated in a short time window. As shown in the figure, frames 19 to 22 are all selected without the distance penalty, but only 20 and 21 are selected when distance cost is applied. Finally, with user-specified priorities and a number of time steps to display, we minimize the weighted sum of these cost functions and choose the optimal sequence as salient time steps. The cost matrix of each cost function is displayed here in the figure. To facilitate interactive exploration of geospatial data, we integrate our approach into a web-based system. The user interface consists of 4 components. The map view displays heat maps for current data. The timeline view facilitates temporal selection and exploration. Users set a focus range and navigate between time steps with the help of contextual visualizations, including the temporal trend and the relative trend. The thumbnails for selected salient frames are listed on the top for reference. 3 function panels are provided on the bottom, allowing users to label or unlabel salient frames, performing temporal navigations, and controlling playback. The control view allows users to specify priorities and parameters for time selection. The dimension-reduced latent space offers additional information about data variations, helping users identify crucial events. The playback view utilizes locally cached frames for cyclic data playback, offering dynamic insights. Now, we use our system to inspect Hurricane Dorian. We use data from the ABI instrument of GOESR satellite, showing the TOA brightness temperature from August to September 2019. Given hurricanes cause drastic TOA brightness temperature drops, we focus on mean aggregation. Now we can swiftly obtain the overall variations of the data. The temporal trend shows a trough on August 25th, marking the formation of the tropical wave. Zooming in the timeline, we narrow down the focus range. We can see the evolution of the hurricane eye and its northward movement along the US East Coast. By inspecting the trajectories in the latent space, we can navigate to these turning points to see the important structural changes of the data. The relative trend helps identify the frames with significant deviations of minimum values from current frame. For a closer look at the hurricane's eye, we switch to regional mode by selecting a spatial boundary on the map. Playback, preview, contextual visualizations, and salient frames are now generated within the spatial boundary. The temporal trend now reveals a drop of brightness temperature to about 200 K on September 2nd. Our approach is evaluated on 5 real-world datasets. We evaluate the summarizability of the selected frames using the reconstruction error of their piecewise linear interpolation results. In most cases, the frames selected using our method exhibit better reconstruction quality compared with even selection and the previous method. Our method can also effectively reveal the evolving patterns in the data and achieve more stable selection results. The extremums and outliers in the datasets are also selected, providing users with insights into temporal patterns or data quality. We also conducted a usability study with the same group of experts in our need-finding study using an adapted version of the system usability scale. The results show that our system can provide users with a better experience for temporal selection and data exploration with a small learning effort. In summary, SalienTime makes temporal navigation and selection in geospatial systems context-aware, offering users with a smooth experience and informed decision-making workflows when accessing large-scale geospatial data. For more details, please refer to our paper and source code, and thank you for your listening.